All right, silly people, here's the situation. We're going to be doing a proof. We're going to be proving that the probability that you find a particle between the points A and B, um, when you take the derivative of that, it's equal to this probability density stuff subtracted by each other, where the probability density is defined there. And then in the second part of the problem, we're going to calculate the probability density of this wave function, which we found in problem 9. So, okay. Um, First of all, probability distribution, or not even the probability distribution, just the probability that you find a particle between the points A and B, um, is given by the integral from A to B of the square modulus of the wave function over position. So if you take the time derivative of that, you get dp dt is equal to d dt of the integral from a to b of, yeah, it's just the time derivative there. Funky thing is you can move that time derivative into the integral in the form of a partial derivative. Now we have partial derivative with respect to time of the square modulus over position, and then this is a interesting formula from Griffiths. That quantity is given by this relation, del psi squared del t is equal to the partial derivative with respect to x of I h bar over 2m psi star del psi del x minus del psi star del x psi. All right. So we can use that relationship here. Just plugging it into our integral, we have that the time derivative of the probability now is looking like the integral from a to b of the partial derivative of this junk with respect to position. And integrating that over position. What's cool is that now we have a partial derivative of the stuff that's in our integral and we're integrating over it. So that's just going to be equal to the stuff in the brackets evaluated at the bounds. It's a little bit of a fundamental theorem of calculus there, I guess. Yeesh. Del x minus del psi star del x psi from A to B. And then, so in great detail, let's just plug in our values for A and B. And let's actually go ahead and flip the sign on each of them. So we're going to have IH bar over 2m. We're going to do A first because we're flipping the signs. Psi star A del psi del x evaluated at A. And this should actually be, I'm jumping the gun a little bit here, psi A, psi star A minus psi star A del psi del x evaluated at A. And then we have minus I h bar over 2m. We got psi of b times the derivative of psi star evaluated at b minus psi star b del psi del x evaluated at b. And these guys actually match the definition of the probability current that the problem gave. So it's looking like that. So there you go. The next bit is to actually turn the wave function from problem 9, this guy, into a probability current. So let me just copy that down. Okay, the probability current of this wave function is going to be something that's really long to write. It's going to be I h bar over 2m open bracket. We're going to have the normalizations of 2am pi h bar, the 1/4. Exp, going to go ahead and move the a into the rest of it, so minus amx squared over h bar minus iat. Oh my goodness. And then the constant again, pi h bar to the 1/4, and then times the times the position derivative of the complex conjugate of this thing, which just puts a plus sign on the IAT stuff. Okay, and then minus the conjugate wave function. So this stuff, and you'll have plus IAT, and then times the derivative of the wave function, which is that. You can probably already tell that the time components are going to cancel out. And then just moving right along, we're going to factor out the square root 2am over pi h bar stuff. And then what we're left with in here is just exp minus amx squared over h bar, and then that derivative is minus 2amx over h bar exp amx, or minus amx squared over h bar. Then we have minus exp minus amx squared over h bar minus 2amx over h bar exp to the minus amx squared over h bar. And hey, they cancel out because these two big terms are the same, like that. So turns out the probability current for this wave function is 0. Fun.